We are very fortunate to have today Professor Lu giving us this keynote talk. She will be presenting it from China. I hope everything will work. We have tested it. So she is a professor in the Department of Computer Science and Engineering at Sun Yat-sen University. She also serves as the director of the National Supercomputing Centers in Guangzhou and Shenzhen. Professor Lu specializes in HPC with research interests spanning advanced computer architecture, programming models, and parallel computing environments. She was the deputy chief designer of the Tianhe 2 supercomputer. She currently serves as the chief designer of the LineShine exascale supercomputer. As many of you know, this system is the #1 in the world now. And Professor Lu has designed that, so that's what she will be talking today. So throughout her career, Professor Lu has been dedicated to bridging high-performance computing with major scientific and engineering applications. She has helped make advanced computing capabilities more accessible to a broader community of researchers and industry users. Professor Lu has been recognized as an ISC Fellow and CCF Fellow. She has also led multiple major research projects supported by the MOST and the NSF-C program. Those are the programs in China. Her current research focuses on cutting-edge computer architectures and the convergence of advanced AI and HPC systems and applications. So I think Professor Lu, you can turn on your video now. And please share the slides.
Good morning, everyone. It's a great pleasure to have a chance giving talk at Mark 26. Thanks, DK, for inviting me. It's a pity that I couldn't be there in person to meet you all. I hope we have another opportunity next time. Today, I will talk about converged computing with LineShine. In recent years, the rapid rise of AI has brought significant pressure to supercomputing centers, especially in China. Actually, the broader question is, well, supercomputing should go next. AI is reshaping both the technology landscape and application patterns. For supercomputer centers, this brings new challenges, but also new opportunities. Our mission remains the same: to meet real needs in scientific discovery and engineering innovation, and to provide efficient, reliable, and sustainable computing support for our end users. In this talk, I will show our work on constructing the new supercomputing system, LineShine, at the Shenzhen Supercomputing Center over the past few years, sharing our practices, main progress, and views on new generation converged supercomputing systems and applications. I will move from the broader trend to the new LineShine system architecture, communication, and software, then to application cases, followed by a brief summary. Over the past decade, both supercomputing and AI have continued to scale from systems to applications. On the system side, HPC has moved from petascale to exascale, from Tianhe 2 to EI Captain. Sustained FP64 performance has increased by roughly 50 times, reflecting the difficult post-Moore trajectory of high-precision scientific computing. In parallel, AI systems have scaled even faster. FP16 low-precision AI throughput has grown by more than 500 times, often described as Huang's law. On the application side, scientific computing is moving toward larger simulations, higher resolution, and more complex multi-domain workflows. Golden Bell applications have achieved about 150 times performance improvement scaled to tens of millions of cores, and reached beyond exaflops performance also. Meanwhile, AI models have grown from millions to trillions of parameters, with training resources expanding from hundreds to hundreds of thousands of accelerators. The key message is clear. Sustained scalability in next-generation supercomputing requires both mixed precision and HPC AI convergence at the system and application level. Supercomputing makes complex scientific problems computationally tractable. Scientific applications are inherently multi-scale and dynamic, spanning from atoms and molecules to Earth systems. Over the past 40 years, numerical simulation has become indispensable for scientific discovery and engineering innovation. As application scale grows, computing demand is outpacing system capability. AI can help reduce dimensionality, build fast approximation models, and improve data assimilation and support optimization. But low-precision AI cannot simply replace scientific computing. High-fidelity simulation remains essential for physics correctness, validation, and trust. AI should complement and extend this foundation. From the application perspective, the key question is how HPC and AI should be coupled to solve real scientific and engineering problems. Based on a broader study of domain applications, we proposed 3 representative coupling patterns. The first is the surrogate pattern, where AI replaces selected expensive components with fast approximations, useful for repeated simulations, parameter exploration, and uncertainty analysis. The second is the directive pattern, where AI gets HPC simulations by selecting parameters, steering search directions, and optimizing workflows, and high-fidelity computation remains on the HPC side. The third is the coordinate pattern, where AI and HPC work in tandem, continuously exchanging data, predictions, and feedback. This is especially important for complex workflows, may involving large language models, scientific foundation models, and AI agents. These patterns help structure HPC AI convergence at the application level and guide future hardware and software design. Supercomputer evolution has always been shaped by applications, algorithms, and architectures. From the architecture perspective, the central question is how to accelerate computation more efficiently. Systems have evolved from vector, SMP, and MPP architectures to CPU, GPU heterogeneous architectures, while accelerators are usually attached as external devices. This has brought major performance gains, but also more complex programming models, heavier data movement, and higher software migration costs. As HPC and AI become more tightly coupled, matrix computing is moving closer to the CPU. Technologies such as ARM-SME represent an online acceleration model with scalable matrix engines integrated directly into the processor architecture. This improves programmability, reduces data movement, and makes online acceleration an important direction for future converged supercomputing. Post-exascale supercomputing can no longer be designed around peak flops alone. The real target is system-level balance and application-level convergence, with computation, energy, memory, network, storage, and software co-designed as one system. The goal is to support high-fidelity simulation, scientific data services, AI training and inference, and automated discovery in an integrated workflow, turning nominal system capability into real scientific and engineering productivity. Over the past few years, with the support of Shenzhen municipal government and the joint efforts of our project team and partners, we have developed a new supercomputing system, LineShine, with got the top one at this year's top 500 list. Our system design principles are ABC: application-driven, balanced architecture, and co-design on full stack. We pursue high performance, high power efficiency, and high programmability. Here is the processor to system view. Each node contains 2 domestic CPUs, delivering about 120.6 teraflops. 8 nodes form a blade, 16 blades form a frame, and 2 frames form a cabinet, reaching about 30.87 petaflops per cabinet. At full scale, LineShine integrates 90 cabinets, over 22,000 nodes, and more than 13 million cores. It has achieved 2.198 exaflops sustained FP64 performance within 42 megawatts. Power efficiency is 52.07 gigaflops per watt. It's a quite balanced system. We propose a new online acceleration CPU-only architecture that inherits the HPC tradition, embraces the AI-driven future, and returns to the essence of computational acceleration. In our LX2 CPU design, matrix acceleration units are integrated on chip, actually on cores, greatly reducing data movement, overhead, and improving programmability. The LX2 CPU, equipped with 304 cores and high bandwidth memory, it supports the ARM ISA, delivers mixed multi-precision computing capabilities. A single CPU delivers up to 60.3 teraflops of FP64 performance with a power draw of 690 watts. The CPU also integrates HBM with around 4 terabyte per second bandwidth, supporting both cache mode and flat mode. The HBM DDR unified memory design balances capability and bandwidth for different application patterns. Its chiplet architecture integrates 2 CPU dies, 8 HBM dies, and 4 I/O dies together across different process technologies. This design improves integration, reduces power, and lowers footprint for diverse HPC AI workload. At exascale, the interconnect is critical for scaling application performance beyond individual nodes. LineShine implements the Lingqi high-speed interconnect network with innovations in chips, switches, and communication protocols. It adopts a 4-layer factory top-load. It connects compute nodes and I/O components and can scale at to 100,000 nodes and 2 million ports, delivering 3.5 petabit per second bisection bandwidth and 1.07 microseconds minimal latency. Reliability and availability are supported by lossless communication, dual-plane and multi-rail networking, multi-level redundancy, and production scale management mechanisms. The storage system is tiled. It provides performance tile and capacity tile while maintaining a unified data path. The performance tile supports active drops, staging, and high throughput workflow phases. The capacity tile supports retention and code data. The distributed file system provides scalable metadata and a shared namespace. 200 petabyte currently configured, with expansion to 1,000 petabyte planned within this year. The practical goal is to balance bandwidth, capacity, and cost. For HPC AI workflows, storage is part of the computational pipeline. It directly affects data ingestion, checkpointing, training data access, workflow migration, and lifecycle management. LineShine's software stack unleashes hardware capability. We provide custom OS, various libraries, optimization tools, OpenMP, MPI, PyTorch, as well as domain-specific tuning. The scheduler and the management system support diverse workloads, topology-aware scheduling, and production-grade operations. The goal is a unified software environment that is easier to program, optimization, and operate at scale. Although SME provides powerful on-chip matrix acceleration, real application performance still depends on optimized middleware. Across HPC and AI workloads, such as tensors, gym, graph computation, and attention, we need to transform computation patterns, coordinate SME and SVE execution, and manage memory placement effectively. Our work focuses on this middleware layer. We reformulate key kernels into SME-friendly matrix operations, use SVE for row-wise and irregular parts, and optimize HBM DDR placement, cache blocking, tile packing, and precision to reduce data movement and improve reuse. The results show clear gains for stencil kernels, gym, and attention. These studies have been published on the conference of SC last year. Data in Europe are actually this year, showing that software optimization is essential. I would like to share a little more information about the communication scalability of the LineShine system. The link-key interconnect begins by shortening the data path between the processor and the network. The NICs are integrated into the I/O dies of the LX2 CPU package, and each compute node provides 8 network interfaces. This package integrated NICs can directly access both HBM and DDR for RDMA communication, avoiding an external PCIe device path. At the system level, LineQi adopts a 2-plane 4-rail factory topology. The connection from L1 to L2 is no blocking. The L2 to L3 layer uses a 16:3 oversubscription ratio, and the connection from L3 to L4 is again no blocking. On top of this topology, LinQi supports both oblivious and adaptive routing. Physically, only the L2 to L3 connections use optical fibers. All other connections are implemented through direct plug orthogonal backplines, reducing internal cabling and supporting high-density system integration. In this architecture, switch borders are arranged orthogonally and connected directly through high-speed connectors. This eliminates the need for the conventional backplane and removes optical modules from short distance switch-to-switch connections. The dual plane and multi-rail organization provides both aggregate bandwidth and redundant communication passes. As a result, the design reduces optical module power consumption, lowers single conversion losses, simplifies system cabling, and maintains high bandwidth, low latency communication. On top of the hardware, LinQi provides a customized OpenMPI implementation together with UCX and UCG support. LinQi delivers more than 3.5 petabits per second for full system bisection bandwidth. The single hop latency, again, is 1.07 macroseconds, while the latency between the farthest endpoints is 2.59 macroseconds. The OSU bandwidth test measures an aggregate bidirection bandwidth of 381 gigabytes per second per node. The MPI graph test results show an average bandwidth of over 44 gigabytes per second for 128 nodes within a single frame and approximately 19.5 gigabytes per second for 256 nodes spanning 2 frames. For reliability, LinQi combines credit-based lossless floor control with per link CRC verification and link local retransmission. Beyond conventional MPI, UCX, and UCG, we also provide 2 extended communication semanticals, UNR and SDT. They expose useful hardware and protocol capabilities while encapsulating the complexity of low-level network operation. UNR, or Unified Notifiable RDMA, carries an distinguishable completion notification within the RDMA operation itself. In a conventional implementation, transferring the data and confirming a remote completion may require separate operations. With UNR, the target can observe the completion event when the data arrives, eliminating an additional synchronization exchange. SDT, or Stream Data Transfer, targets applications that continually generate data. It pre-registers a shared memory pool and divides that pool into reusable block buffers. The sender obtains a block, fills it, and transmits it. After the receiver consumes the data, the block is released and reused. This design reduces memory registration and buffer management overhead. It also avoids repeated communicator and tag matching in high-frequency streaming workloads. Let me take HPL as an example to explain our MPI-related optimizations. The mainly include three aspects. First, we optimized the MPI processor layout and resource mapping by moving from one processor per NUMA domain to one process per die. We reduced the panel broadcast data volume by half and decreased the message count from 8 to 2. This also increased the available HBM capacity per MPI process by 4 times and reduced the total number of processors from about 400,000 to about 100,000. As a result, MPI communication and synchronization overhead will significantly reduce. Second, we optimized computation and memory placement around DGEM. Since DGEM dominates HPL performance, we used it as a design center. We placed communication buffers in HBM and used HBM as a high bandwidth staging buffer, reducing data movement between DDR and HBM and improving the efficiency of matrix updates and panel processing. Third, we optimized MPI communication on the interconnect network. We adopt topology-aware MPI ring mapping and optimized panel broadcast algorithms, including ring-based and topology island broadcast schemes. These optimizations make the MPI communication pattern better match the physical network topology, reducing long-distance communication, alleviating congestion, and improving HPL scalability at full system scale. For the full populated 90 cabinets deployment, using the test parameters shown here, LineShine achieved a sustained HPL performance of 2.1984 exaflops, our max against our theoretic peak of 2.74 exaflops, our peak, delivering a computational efficiency of 80.35%. The residual error remained within the required accuracy bound, confirming numerical correctness under a full system power draw of 42.222 megawatts. Scalability tests from 6 to 90 cabinets further verified stable efficiency after system-level tuning. Across all dies, DGEM efficiency remained tightly clustered between 91% to 92%, demonstrating balanced hardware utilization, consistent silicon performance, and effective software scheduling with no weak computer units observed. We have tested multiple benchmarks beyond HPL, including HPCG, HPL MXP, and Graph 500, covering different computing scenarios. All of them achieved strong performance, demonstrating the balanced design and high efficiency of our hardware and software architecture. With the system architecture established, I now move to applications. Since LineShine was deployed at the end of last year, applications from multiple domains have been steadily ported, developed, and executed on the platform, covering climate, CFD, earthquake simulation, materials, energy, drug discovery, neuroscience, scientific AI, and more. So far, we have supported over 24 system-scale applications across diverse scientific and engineering domains. More than half of them already used mixed precision and incorporated AI methods, showing the growing convergence of HPC and AI in real applications. I would like to show a few application cases. This case addresses a fundamental science question in war turbulence. How near-war statistic behavior at very high friction Reynolds numbers. Reliable high Reynolds DNS data are needed to distinguish between competing scaling interpretations. The challenge is cost. Higher Reynolds requires larger grids and longer production runs, with overall cost scaling roughly as Reynolds to the fourth power. To make this feasible, we designed an application program power law and core-optimized computation, memory, and communication on LineShine system. SME and SVE are used for high-order denser kernels. FP32 storage is combined with FP64 critical path computation, and transpose communication is reduced and localized through topology-aware rank mapping and one-side communication. Achieved production DNS beyond Reynolds of 20,000 and ongoing extreme case towards Reynolds of 43,000, reaching the largest public documented production scale war turbulence DNS. We also explored AI acceleration as a potential path to improve end-to-end time solution. Furthermore, this slide shows how UNR is used to pipeline communication in power laws, pressure passing equation solver. The solver contains two global transportations, one from the X pencil decomposition to the Y pencil decomposition, and another from the Y pencil back to the X pencil decomposition. Each transposition involves an O2O exchange using a dedicated buffer. The transportations are first decomposed into fine-grained slabs. As soon as a thread finishes the X direction FFT for one slab, it immediately transfers the slab through UNR. At the receiving process, the arrival notification allows another thread to begin the Y direction FFT on that slab immediately, without waiting for the completion of other slabs O2O operation. Communication and computation therefore proceed as several interleaved pipelines. On LineShine, this fine-grained pipeline hides 70 to 74% of the original transpose communication time. Another case, here is another case. We designed and implement a biologically constrained whole brain simulator for human skull brain dynamics. We call it cerebrosome. It converts MRI-derived brain structure and connectivity into executable spiking neural networks at neuron and synapse resolution. By developing delay-aware spike broadcast, race-free synaptical dynamics, and sparse synapse compression, cerebrosome achieved the largest whole brain simulation to date, scaling to 86 billion neurons and 100 trillion synapses. This provides a practical platform for studying neural mechanisms, brain disorders, and brain in-spiral computing at whole brain scale. Furthermore, a cerebrosome has a very different communication pattern. Neuronal spikes are sparse and irregular, and different synaptic connections have different biological transmission delays. Directly sending many small messages from every process to all destination processes would create fragmented communication and poor network utilization. Cerebrosome uses SDT-based streaming communication. Pre-registered memory and reusable buffers reduce the management overhead of continuous spike transmission. On top of SDT, the delay-aware spiker broadcast layer performs three operations: aggregation, routing, and distribution. Spiking communication is reorganized as aggregated hop-by-hop forwarding over a configurable virtual topology. The example shown here uses a three-dimensional HyperX topology. Intermediate nodes can combine spikes that show the same forwarding direction, reducing number of fine-grained messages and improving link utilization. Cerebrosome also exploits the biological delay associated with each spike. Spikes with zero or very short delays are prioritized for immediate transmission. Spikes with longer delays can be aggregated or forwarded within their permitted time windows. In this way, communication can overlap with neuronal computation while preserving the required spike arrival timing. In material science, first principles simulation is one of the most important tools for understanding atomic and electronic behavior. Among these methods, quantum density functional zero, or DFT, is widely used because it can provide electronic structure information with high accuracy. But the challenger is scale. Conventional quantum DFT has cubic computational scaling and quadratic memory scaling. So in practice, it has usually been limited to a few hundred and a few thousand atoms. The correspondence to only a few nanometers. For many real materials problems, such as solid-solid interface in all solid-state batteries, the experimentally relevant region is much larger, often tens of nanometers and millions of atoms. This is why there has been a major gap between quantum simulation and experimental observation. To address this, we developed XLS DFT, a linear scaling DFT framework for exascale supercomputing. The core idea is a divide and conquer decomposition of the one particle density matrix. Instead of solving one global edge problem for the whole system, we decompose the system into many local subsystems and solve them independently. Each subsystem is solved using Chebyshev filter subspace iteration, or Chebyshev, and the electronic observables are assembled from these local solutions. XLS DFT is optimized for the LineShine exascale system. We use SVE and SME optimized kernels to accelerate the finity difference stencil operations and dense linear algebra. The results are shown on the right side. We achieved a 100 million atom silicon system, which is 10 times beyond the previous DFT record. Using more than 12 million CPU cores, we also applied it to an 11 million atom Li LGPS battery in interface. For this battery system, the larger scale DFT calculation revolves low volume germanium near the interface, and this agrees well with the XPS measurement shown here. So the key message is that XLS DFT moves Kwangshan DFT from nanometer scale idealized models to experimental relevant million atom material systems. This work has been selected as a finalist for the 2026 ACM Golden Ball Prize. This slide presents our HPC AI workflow for device scale scanmuon formation, important for magnetic storage, spintronic devices, and lower power information technologies. Scanmuons are nanoscale spin textures, but device-relevant simulation requires micrometer scale domains and the explicitly coupling between lattice motion and spin dynamics. AI provides the spin lattice potential, reducing complexity from ON triple to ON, while HPC enables trillion scale atom spin simulation. On LineShine, the workflow reaches 1.34 trillion atoms and spins, with about 90% weak scaling efficiency on more than 12 million CPU cores. This enables direct observation of scanmuon formation at device-relevant scale, showing the value of extreme scale computing for previously inaccessible physical processes. This slide presents our 10 trillion scale synthesizable drug screen application. The goal is to identify multi-target drug candidates with balanced scale, synthesizability, and physical fidelity. Pure HPC scaling is too slow, while pure AI needs physical validation. At the system level, millisecond AI inference and hour-level HPC simulations also creates severe load imbalance. We developed a self-involving HPC AI framework where reaction template constraints issue synthesizability. Reinforcement learning gets the search. High-fidelity simulations provides validation. And RTAI deposes AI and HPC tasks through asynchronous hierarchical scheduling. With this framework, we completed high-fidelity screen at 10 trillion scale in 22.6 hours on full LineShine system and identified IND-ready anti-cancel candidate heats. High-resolution kilometer scale global climate simulation is a ground challenger workload for large-scale supercomputing. It covers atmosphere, ocean, land, and ice prediction, and supports larger ensemble data assimilation and 30-day global 1 kilometer forecasts. In this application, AI-based physical parameterization replaces selected expensive components, reducing compute costs by 32% while maintaining physical consistency. Using FP16 mixed precision, exascale I/O pro-processing, and load balancing further improves throughput and scalability. As a result, we achieved new 1 kilometer simulation records: 1.73, 3.08, and about 1 similar year per day for atmosphere, ocean, and the copper system, respectively. Here are a few more examples. We implemented the first trailing-grade real earthquake simulation. We achieved one of the largest takeoff and landing airplane simulation with 1 trillion degrees of freedom and 10 billion cells. In universal MLIPS, we achieved 1.2 exaflops for AI training. In generative composition for Earth observation data, we achieved up to 2.16 exaflops for ultra-lower byte rate reconstruction. As you can see, most of these applications are already HPC AI converged workflows. They also demonstrate LineShine's capability for large-scale AI training and inference on a CPU-based supercomputing architecture. So HPC and AI convergence requires more than hardware capability. It needs an efficient, easy-to-use, domain-oriented software stack with consistent interfaces for simulation, data, training, inference, and workflow orchestration. We are building a hierarchical HPC AI software stack like this, and hope to work with more partners to co-develop this ecosystem and translate system capability into real productivity. Today, the most buzzword is token. In China, the average daily token consumption has already exceeded 140 trillion, growing by more than 1,000 times in just 2 years. But tokens ultimately rely on flops and system-level full-stack optimization. Meanwhile, large language models are evolving from dialogue to execution, from general corporal to industry data, and from data-driven modeling to physical interaction. So future AI systems will require mixed precision computing, reliable data services, and strong CPU-based scheduling and execution. This points to triple computing convergence: scientific computing, engineering computing, and intelligent computing, supported by one integrated infrastructure. To summary, I would highlight 4 points. Number 1, supercomputing remains fundamental infrastructure for science, engineering, industry, and AI, and new accelerated computing architectures are still critical. Number 2, HPC AI convergence is becoming the core path for post-exascale applications, especially through closed-loop integrated workflows. Number 3, Real performance now strongly depends on the energy efficiency, data movement, software compatibility, and trustworthiness. Number 4, data and model access will become long-term strategic resources. This is a broader significance of LineShine. It shows how a new generation supercomputing system can be driven by application requirements, validated by full system workloads, and positioned as a convergent platform for scientific intelligence computing. The last slide is a photo of our LineShine system. Its Chinese name LineShine carries symbolic meanings. Lin means intelligence, and Sheng combines sun and success, reflecting our best wishes for the system. I will stop here. Thank you.
Thank you. Let's give a big hand to Professor Lu. We have time for several questions. Anybody here? Yeah, I think let's bring Professor Lu's screen. I think. Yeah, so Professor Lu, you can hear us, am I right? Yeah.
Okay, yes,
Yeah.
I can hear you. Hi.
Yeah. Okay. So yeah, Dan is here. So Dan will be the first one to ask question. Yeah.
Yutong, Stan Zion from Texas Advanced Computing Center. Thanks for the fantastic talk. It seems like in your design, you're still prioritizing 64-bit computation, whereas a lot of the US chip manufacturers have moved away from 64-bit because of the focus on AI. How much 64-bit workload do you still see in the mix of what runs on LineShine?
I think it's, our supercomputing center use LineShine and mainly for the scientific computing. We have more than 60% of the computation done by, FP64, and also more and more AI workloads coming, from different or various domains. So you can see the examples I give you in my talk. There are also focus on the scientific and engineering application, but we involved also the AI methods, including training and inference. And also we use, the FP32 or FP16, the computational power to help the scientific computing. Yeah, so, I think in the supercomputing center for the scientific and the industry application workloads, we still need FP64. And also, we may involve more and more low precision computing power to support our scientific and industry application to, including the new AI methods or lower precision computation. Yeah.
Thank you very much. I'm very jealous of your 64-bit performance.
Any more questions? Yes, please use that. Yeah.
On your storage design, I didn't see like what what file system are you using on top of that? Is it homegrown?
Yeah, it's our custom file system. Yeah, it's it's a hierarchy storage system. We have the we have the performance layer and also the capacity layer. And for the file system, we use the distributed file system designed by ourselves, and it's not similar with the Alaster, because I think its main difference is we have a distributed metadata. Yeah, it's you know, we call it a distributed metadata and distributed the storage service. So yeah, we combine, you know, the performance and the capability together. And we also consider the HPC and AI converged the requirement of the various application models. Yeah, we try to fulfill the different IO models requirements. Yeah, to balance the performance and also balance the throughput.
We have an online question. Pankaj, please, I think you can be unmuted and ask question. Yeah.
Yes, DK, thank you. And Dr. Lu, this is excellent talk. I was particularly fascinated by your memory for communication approach and how you are managing both the notification mechanism for data transfer and the automatic allocation and deallocation of shared memory in the pool. So I was wondering, two questions. One, I was wondering that this is very ready for CXL, and some Chinese supercomputers at Alibaba already work with company like XCon to implement CXL in the AI supercomputer, and I didn't see that here. Second question was for the notification. You must have had the ability to come in from the network and trigger some synchronization object in the operating system. Could you go into a little bit more detail of how that was achieved? Thanks.
Okay. For the first question, we didn't use a protocol with CXL. Yeah, at this system, we have the HBM and DDR cloud memory in computational nodes. So we use the HBM as well as the DDR to do the shell memory when we do the message parsing, respectively, depending on the communication protocol. So no, like Alibaba you mentioned, we haven't used the CXL yet in this system. And for notification part, the UN, I guess you may talk about the UNR protocols I mentioned in my talk, right?
That's right.
Yeah. So the notification part we use, it's I think it's for the software and the register setting part. So it's not directly from the hardware part. It's actually it's a register and the memory buffer chat. Yeah. If you need some more details, I will maybe I can send you a one paper to say, yeah, we published a paper in SC 24. Yeah, you can, maybe you can send that. And it's not in this machine, but the similar protocol and methods we provided. Yeah.
Yeah. May I ask a follow-up on the UNR
sure.
part?
Sure.
So are you having to implement some kind of efficient polling of those registers to pick up the notification in a timely way?
I think I'm not quite clear your question.
Question is about CPU.
Yeah.
So if you have triggering of register from the network to issue notification, then is the CPU having to efficiently poll that register to achieve timely notification?
Yeah. Actually, the need to pour one of the registers and to see that I think it's a register may trigger the notification. Yeah.
Okay. Okay. I'll read the SC24 paper. Thank you so much for your talk.
Thank you.
Are there any other quick questions before we move on? Any questions from online? Okay, so if not, let's give again a big hand to Professor Lu.
Thank you.
So thanks, Professor Lu. I know it is late evening there. Sorry we couldn't have you in person. Might be next time.
Okay, thank you.
We'll go and just for everybody's information, Professor Lu had an event